For most of human existence, the night sky rested above the Earth as a quiet constant. Long before engines, satellites, or metal towers, people stood beneath open air and observed the steady glow of distant stars. In deserts, forests, river valleys, and along coastlines, generations watched as constellations returned in familiar patterns. The moon shifted gently through its phases, waxing and waning in a rhythm that marked time without urgency. A few wandering lights, later understood as planets, moved slowly against the fixed background of stars. These early observations were careful and patient. Farmers noted seasonal changes in the sky to guide planting and harvest. Seafarers memorized star positions to navigate across dark waters. Scholars in ancient cities pressed markings into clay tablets, recording planetary paths with quiet precision. Over centuries, these records accumulated, allowing patterns to emerge gradually. The heavens, once interpreted through stories and symbolism, began to be described through measurement and calculation. The development of optical instruments expanded human sight. Telescopes revealed that the moon carried mountains and shadows. New planets were identified beyond those visible to the naked eye. Moons were observed circling distant worlds. The sky no longer seemed smooth or unreachable. It appeared textured, physical, governed by motion and consistent laws. As understanding deepened, Earth itself was recognized as one planet orbiting the Sun. This shift in perspective unfolded slowly across generations of study. With it came a quiet transformation in imagination. If celestial bodies were physical places, governed by gravity and motion, then travel, once the subject of poetry and fiction, could be considered through mathematics and engineering. Long before rockets were constructed, thinkers explored propulsion and theory. Equations described escape velocity. Concepts of thrust and fuel were outlined carefully on paper. For many years, these ideas remained abstract, resting in notebooks and academic discussions. Space travel began not with flame or thunder, but with centuries of steady observation beneath a calm and patient sky. As scientific understanding matured, the idea of leaving Earth gradually shifted from imagination to structured theory. During the 17th and 18th centuries, scholars refined the laws of motion and gravity. Careful experiments demonstrated how force could move an object, how resistance slowed it, and how gravity drew it back toward the ground. These principles were not developed with spaceflight in mind, yet they quietly formed its foundation. In the 19th century, technological progress accelerated. Steam engines, industrial manufacturing, and advances in metallurgy reshaped transportation on land and sea. Engineers learned how to construct stronger materials and more reliable engines. Meanwhile, scientific societies published detailed studies of energy, combustion, and propulsion. Thoughtful inventors began considering whether controlled explosions might produce sustained thrust. Among these early thinkers were individuals who examined rockets not as fireworks, but as vehicles. They studied how expelled gas could push an object forward in the opposite direction. This principle, described by earlier physicists, required no air to function. It suggested that propulsion might continue even in the emptiness beyond the atmosphere. In quiet workshops and academic offices, calculations accumulated. Diagrams showed multi-stage rockets, in which empty fuel sections could be discarded to reduce weight. Liquid fuels were proposed as more efficient than solid powders. These concepts remained theoretical for many decades, often dismissed as impractical or overly ambitious. Funding was scarce, and public interest remained focused on aviation and terrestrial industry. Yet the groundwork continued to develop steadily. Scientific journals preserved the mathematics of thrust and trajectory. Small experimental rockets were tested in open fields, rising modestly before returning to Earth. Each attempt added data, refining understanding incrementally. By the early 20th century, the possibility of reaching space no longer belonged solely to fiction. It rested within equations, material science, and patient experimentation. The path forward was still long and uncertain, but it had begun to take measurable form. In the early 20th century, theoretical exploration began to shift toward practical experimentation. A small number of engineers and physicists dedicated themselves to transforming mathematical models into working machines. Their laboratories were often modest, sometimes little more than sheds or open fields, yet their ambitions extended far beyond the horizon. One significant development during this period was the refinement of liquid-fueled rockets. Unlike earlier solid fuel designs, liquid propulsion allowed for greater control and efficiency. Fuel and oxidizer could be stored separately and combined in a combustion chamber, producing sustained thrust. The idea required careful engineering, including pumps, valves, and stable fuel mixtures. Early prototypes were fragile and frequently unreliable, yet each test provided valuable information. In various countries, independent researchers conducted experiments with limited resources. Small rockets rose briefly into the sky, tracing thin arcs before returning to the ground. These launches were quiet compared to later space missions, yet they represented meaningful progress. Careful records were kept, noting altitude, burn duration, and structural stability. Adjustments followed each attempt, improving performance gradually. Public attention during this era remained focused primarily on aviation. Airplanes were becoming faster and more dependable, capturing imagination and investment. Rocket research, by contrast, often seemed distant from practical application. Nevertheless, a few scientific communities recognized its potential. They organized societies devoted to astronautics, published technical papers, and exchanged ideas across borders. As global tensions increased in the 1930s and 1940s, governments began to take greater interest in rocket technology. Military funding supported further development, accelerating advancements in propulsion and guidance systems. Though these efforts were shaped by geopolitical realities, the underlying engineering knowledge would later contribute to peaceful exploration. By the middle of the century, rockets had grown more powerful and more reliable. The technical foundation for reaching beyond Earth's atmosphere was approaching readiness, built through decades of patient refinement and persistent experimentation. By the mid-20th century, rocketry had evolved from scattered experimentation into organized national programs. The engineering challenges remained substantial, yet propulsion systems were becoming more powerful, and guidance mechanisms more precise. Larger launch vehicles were constructed using improved alloys and carefully tested fuel combinations. What had once been fragile prototypes were gradually replaced by structured, multi-stage rockets capable of sustained ascent. In the years following the Second World War, technological expertise spread across several nations. Engineers studied captured hardware, analyzed performance data, and refined existing designs. Research facilities expanded. Wind tunnels, engine test stands, and telemetry systems were developed to measure flight behavior with increasing accuracy. Each launch generated detailed information about thrust, stability, vibration, and atmospheric resistance. During this period, the concept of placing an object into orbit moved from theoretical discussion toward practical planning. To achieve orbit, a rocket would need not only vertical lift but sufficient horizontal velocity to continuously fall around the Earth without returning to the surface. This requirement demanded precise calculations and reliable staging. Even small errors in angle or timing could prevent success. As development continued, scientific goals began to accompany military interests. Researchers proposed launching instruments above the atmosphere to measure radiation, temperature, and cosmic particles. The upper layers of the sky, once unreachable, were now seen as regions open to systematic study. By the mid-1950s, preparations were underway for attempts to send artificial satellites into orbit. The idea was presented publicly as part of international scientific cooperation, reflecting a growing awareness that space could serve research as well as defense. Engineers worked methodically, refining guidance gyroscopes and strengthening structural frames. The moment when a manufactured object would circle Earth was approaching steadily. It would represent not a sudden leap, but the culmination of decades of measured engineering, calculation, and incremental improvement carried forward by many hands. In October of 1957, a small polished sphere began circling Earth. It emitted a steady radio signal, simple and repetitive, as it traveled silently above oceans, forests, and cities. This object, later known as Sputnik 1, marked the first successful placement of an artificial satellite into orbit. Though modest in size, it represented the practical confirmation of decades of engineering theory. The launch vehicle that carried it upward had been carefully assembled in stages. Each section ignited in sequence, lifting the payload higher while shedding empty mass along the way. The mathematics behind orbital insertion had been studied extensively, yet translating calculation into reality required extraordinary precision. The rocket needed to accelerate the satellite to a horizontal speed great enough to remain in continuous free fall around the planet. Observers on the ground tracked the satellite's passage using radio receivers. Its signal, steady and unadorned, became a reminder that human-made objects could now move beyond the atmosphere. The achievement prompted both scientific curiosity and political response. Governments recognized that space was no longer theoretical territory. It had become accessible through applied engineering. In laboratories and universities, attention shifted quickly toward further possibilities. If a small sphere could orbit Earth, then more complex instruments might follow. Weather sensors, communication relays, and research equipment were proposed. The upper atmosphere and near-Earth space became regions for structured investigation rather than distant speculation. The event also accelerated investment in rocket development. Launch facilities expanded. Training programs for engineers and technicians grew. New agencies were formed to coordinate civilian space research. Within a few years, preparations were underway to send not only instruments, but living beings, into orbit. The quiet radio pulses of that first satellite signaled more than technological progress. They marked the beginning of sustained human presence in the space surrounding Earth, a gradual expansion outward built upon measured calculation and persistent effort. After the first artificial satellite circled Earth, attention gradually turned toward the possibility of human presence in orbit. Engineers and physicians understood that sending a person beyond the atmosphere required far more than propulsion alone. The human body would need protection from vacuum, temperature extremes, and radiation. Life support systems would have to supply oxygen, remove carbon dioxide, regulate pressure, and maintain stable conditions inside a small enclosed cabin. Before astronauts could travel safely, biological research was conducted using animals. Carefully monitored missions carried small living passengers into suborbital and orbital trajectories. Sensors recorded heart rate, breathing patterns, and stress responses. These early flights were designed to answer practical questions about survival in microgravity. Data was gathered methodically, shaping the design of future spacecraft interiors. Spacecraft cabins were engineered as compact environments. Walls were lined with instrument panels, switches, and gauges. Every surface served a purpose. Seats were molded to absorb acceleration forces during launch and re-entry. Windows were small and reinforced, allowing observation while maintaining structural integrity. Each component was tested repeatedly under simulated vacuum and vibration conditions. Training programs also evolved during this period. Prospective astronauts underwent physical conditioning, technical instruction, and simulations that replicated confined living quarters. They practiced operating controls while wearing pressurized suits. Medical teams studied how the body adapted to unusual forces and brief weightlessness. In April of 1961, a human being completed the first orbital journey around Earth. The flight was brief by later standards, yet it demonstrated that people could survive and function in space. Communication systems relayed voice transmissions between spacecraft and ground stations, confirming control and stability throughout the mission. This achievement did not represent an endpoint. It marked another measured step in a carefully constructed progression. The experience gained from that early orbit informed future spacecraft design, mission duration planning, and international investment in continued exploration beyond Earth's atmosphere. As human spaceflight became possible, attention turned toward longer missions and more complex objectives. Early orbital journeys had been brief, designed primarily to confirm survival and basic control. Gradually, mission planners extended duration, allowing astronauts to remain in space for hours, then days. Each additional orbit provided new insight into how the human body adapted to sustained weightlessness. Inside these small capsules, daily life required careful adjustment. Objects did not rest on surfaces but drifted gently through the cabin. Tools were secured with straps and clips. Food was packaged in compact containers to prevent floating particles. Even simple movements required deliberate control. Astronauts learned to guide themselves using handholds along the interior walls. Medical monitoring continued throughout each flight. Heart rhythms, muscle tone, and fluid distribution were studied in detail. Without gravity pulling downward, fluid shifted toward the upper body, altering circulation. Researchers on the ground analyzed this data calmly and methodically, refining exercise routines and cabin design to support longer missions. At the same time, space agencies worked toward rendezvous and docking techniques. For spacecraft to connect in orbit, their speed and trajectory needed precise coordination. This required improved navigation systems, onboard computers, and reliable communication with ground stations. Simulations were repeated many times before actual attempts were made in space. As these capabilities improved, the concept of traveling beyond Earth's immediate orbit began to take structured form. The Moon, visible each night as a steady companion, became a realistic destination. Engineers calculated transfer orbits, propulsion requirements, and re-entry angles. Launch vehicles were scaled upward to carry heavier payloads. The path toward lunar travel unfolded gradually, supported by incremental advances in life support, guidance systems, and propulsion. Each orbit around Earth served as preparation for journeys that would extend much farther. The progress was steady rather than sudden, built on accumulated experience and careful observation. Preparations for lunar travel required not only larger rockets but also new methods of supporting human life over extended periods. Engineers carefully designed spacecraft with separate modules for command, living, and propulsion. Each section served a specific function. One module housed the crew and controls, another contained fuel and engines, and additional compartments were included for supplies, experiments, and re-entry equipment. The arrangement was methodical, emphasizing both safety and efficiency. Life support systems became increasingly sophisticated. Oxygen levels, humidity, and temperature were regulated automatically, while water and food supplies were carefully rationed. Every aspect of the environment was monitored in real time from ground stations. Astronauts practiced controlling these systems under simulated conditions on Earth, learning to respond calmly to anomalies and minor emergencies. These simulations were essential to ensure confidence and competence during actual flight. Rocket engines were scaled up to unprecedented sizes, with multiple stages designed to ignite sequentially. Each stage was tested individually, then integrated into the full vehicle. Engineers calculated thrust, burn time, and payload weight with extreme precision. Even small variations could affect the trajectory, orbital insertion, or re-entry path. Testing was slow and deliberate, with repeated adjustments and careful observation. Parallel to technical preparation, ground-based navigation and tracking systems were enhanced. Networks of radar stations and telescopes were established to monitor spacecraft. Communication systems were expanded to maintain contact with crews at increasing distances. Every orbit, every test flight, contributed additional knowledge about how objects move through space and how signals traveled across thousands of kilometers. By combining these innovations, space agencies gradually constructed the foundation for lunar missions. Each experiment, each test, each orbital flight built upon the lessons of the previous, creating a continuum of knowledge. The Moon, once visible only as a distant companion in the night sky, became a tangible objective. Its position and motion could be predicted precisely, and spacecraft could be guided there with confidence. The realization of reaching another celestial body was no longer an abstract dream, but the natural result of methodical, patient, and cumulative effort, reflecting decades of careful observation, engineering refinement, and the slow, deliberate expansion of human capability beyond the Earth. As orbital missions became routine, attention turned increasingly to the Moon as a destination. Engineers and planners carefully studied the mechanics of transferring a spacecraft from low Earth orbit to lunar orbit, a maneuver known as a translunar injection. Calculations included the timing of ignition, the exact velocity required, and the alignment with the Moon's motion. Even minor errors could result in a missed trajectory, emphasizing the need for meticulous planning and repeated simulation on Earth. Spacecraft intended for lunar travel were designed with multiple modules to manage the unique demands of the journey. The command module housed the crew and flight controls, while the service module contained engines, fuel, and essential systems. Lunar landers were designed to detach, descend to the Moon's surface, and return with precision. Each component was tested independently, and then in combination, to ensure that every interface functioned predictably. Life support remained a central concern. Extended exposure to microgravity required careful monitoring of muscle activity, bone density, and cardiovascular response. Engineers developed compact exercise equipment to help maintain astronaut health. Environmental control systems ensured steady temperature, oxygen, and pressure levels. Redundant systems were incorporated to provide backup in case of mechanical failure, creating a controlled environment within the otherwise hostile vacuum of space. Simultaneously, mission planners focused on navigation and communication. Earth-based stations were expanded into networks capable of continuous tracking and telemetry. Engineers analyzed how signals traveled across vast distances and introduced error correction measures. Flight procedures were rehearsed repeatedly using simulators that replicated the weightless, confined conditions of the spacecraft, allowing astronauts to respond calmly to complex maneuvers. By the mid-1960s, confidence in the feasibility of lunar missions grew steadily. Each orbit, each suborbital test, and each system check contributed to a growing body of knowledge. The Moon, visible nightly to observers on Earth, transitioned from distant imagination to reachable target. The technical foundations were in place: propulsion, life support, navigation, and modular spacecraft design. Every element had been refined through patient experimentation, repeated testing, and incremental improvement. The culmination of these efforts would eventually allow humans to leave the familiar environment of Earth and touch the surface of another celestial body, marking a deliberate and carefully measured expansion of human presence beyond our planet. As preparations for lunar missions advanced, testing and refinement of spacecraft systems became increasingly detailed. Engineers focused on propulsion sequences, ensuring that each stage ignited smoothly and shed weight precisely. These careful measurements were necessary not only to reach lunar orbit but also to allow safe return to Earth. Every launch simulation, every engine test, and every component check contributed incrementally to the confidence required for human travel beyond the atmosphere. Life support systems continued to evolve. Oxygen, temperature, and humidity were controlled automatically, while water and food supplies were carefully monitored. Astronauts practiced managing these systems in simulators that recreated the conditions of space. They learned to move deliberately in microgravity, securing loose objects and adapting to the slow drift of tools and equipment. Daily routines were designed to conserve energy, maintain health, and ensure safety within the confined environment of the spacecraft. Navigation became a critical focus. Translunar injections, orbital alignments, and re-entry trajectories were calculated with precision, incorporating the Moon's position, gravitational forces, and timing for communication with Earth stations. Engineers developed redundancy in both instruments and procedures, so that small errors could be corrected without endangering the crew. Testing extended beyond technical systems to human performance. Physical conditioning, psychological training, and simulated mission tasks prepared astronauts to operate calmly under isolation and confinement. Communication with ground teams was practiced extensively, reinforcing steady procedures and minimizing stress during actual flight. By the mid-1960s, experience from orbital flights, suborbital tests, and rigorous simulations had built a solid foundation for lunar missions. Each successful orbit, each practice procedure, and each incremental refinement contributed to a growing understanding of what was required for a journey to another celestial body. The Moon, once visible only as a distant point of light, was now within the realm of practical reach. The deliberate and methodical progress of engineers, astronauts, and mission planners was steadily transforming imagination into reality, preparing humanity for the first steps on a world beyond Earth. By the late 1960s, preparations for a crewed lunar landing had reached a critical stage. Engineers had scaled up launch vehicles, carefully calculating weight, thrust, and fuel consumption to support both the journey outward and the return home. Spacecraft modules were refined for functionality and safety, with the command module serving as the crew's living and control space, while separate lunar modules were designed to detach for surface operations. Every structural detail, from handholds to instrument placement, was considered thoughtfully to support life in microgravity. Astronauts underwent extensive training to prepare for the unique conditions they would encounter. Simulated missions in full-scale mock-ups emphasize slow, deliberate movement in confined spaces, coordination with mission control, and adaptation to shifting gravity during various phases of flight. Exercise routines and health monitoring were integrated into daily simulations to maintain muscle tone, bone density, and cardiovascular stability, reflecting the knowledge gained from prior orbital flights. Navigation and guidance systems were practiced repeatedly. Translunar trajectories required precise timing, as the Moon itself moved steadily through its orbit. Engineers calculated complex sequences of engine burns, ensuring that spacecraft velocity, angle, and orientation would align perfectly with the planned path. Redundant systems and backup procedures provided safety against small deviations, allowing astronauts to respond calmly to unexpected variables. At the same time, ground-based networks of radar, communication, and telemetry stations were expanded. Engineers monitored simulated flights, recording data to refine procedures and confirm performance. Every practice orbit, every rehearsal of docking or re-entry, contributed to a growing understanding of how to move safely through space while maintaining contact with Earth. Gradually, these efforts transformed the idea of lunar travel from abstract possibility into a carefully structured reality. Each technical refinement, each test of systems or crew readiness, and each rehearsal and simulation prepared humanity for its first deliberate steps on another world. The Moon, visible nightly in the sky, was no longer a distant symbol but a reachable destination, approached through steady, methodical, and deliberate planning. The culmination of careful planning and incremental progress arrived in 1969 with the first crewed lunar mission. Every aspect of the flight had been rehearsed repeatedly, from launch sequences to docking maneuvers, from life support management to re-entry procedures. Engineers and astronauts had worked for years to ensure that each calculation, each system, and each protocol would function reliably in the unforgiving environment beyond Earth. The spacecraft lifted from the launch pad with steady acceleration, its massive engines producing a controlled plume of flame and exhaust. Observers watched quietly, aware that each stage of ascent represented a carefully measured step rather than a sudden leap. The rocket shed empty sections sequentially, lightening the load and maintaining optimal thrust. Inside the command module, astronauts monitored instruments and communicated calmly with ground control, following the rehearsed sequences for translunar injection. As the spacecraft moved beyond low Earth orbit, the Moon's surface grew steadily larger in the window, revealing subtle textures, shadows, and variations in color. Gravity diminished gradually, allowing objects to float and requiring deliberate adjustment of movement. Every tool, every piece of equipment, and even food containers were secured carefully to prevent drifting. Life support systems maintained temperature, oxygen, and pressure at consistent levels, providing a stable environment for the crew. The lunar module separated from the command module for descent, its engines firing in controlled bursts. Touchdown was approached with slow, deliberate precision, guided by careful calculation and constant observation. Every action reflected years of study, testing, and refinement. The Moon, once a distant companion in the night sky, had become a reachable surface, its terrain now accessible to human presence. Throughout the mission, communication with Earth remained steady. Telemetry, voice, and video data allowed engineers on the ground to monitor progress continuously. Each orbit, each maneuver, and each stage of the descent demonstrated the effectiveness of the incremental knowledge and patient engineering that had made human space travel possible. The mission was the natural continuation of decades of observation, experimentation, and methodical expansion into the environment beyond our planet. Upon reaching the lunar surface, astronauts moved deliberately within the confines of the lander. Gravity on the Moon was only about 1/6 that of Earth, allowing steps to be slow, measured, and careful. Each movement was controlled to maintain balance and avoid disturbing delicate instruments or the spacecraft itself. Tools and equipment were secured, with tethers preventing them from floating away. Even small actions, such as adjusting a camera or collecting samples, required forethought and patience. Scientific objectives guided every activity. Lunar soil and rock samples were gathered systematically, stored for transport back to Earth, and carefully catalogued. Experiments were set up to measure surface properties, seismic activity, and solar radiation. Observations were recorded methodically, often in handwriting, as instruments were monitored for subtle variations. The Moon was approached as a laboratory, with exploration conducted slowly to maximize understanding while preserving safety. Throughout the mission, communication with ground teams was continuous. Data on vital signs, environmental conditions, and spacecraft systems was transmitted steadily. Instructions and guidance from mission control were followed carefully, ensuring a collaborative effort between those in orbit, on the surface, and on Earth. Each procedure reinforced the principle that space exploration relies on cumulative knowledge and careful planning rather than improvisation. The lunar landscape revealed textures, shadows, and subtle variations in hue not visible from Earth. Craters, ridges, and plains were observed in quiet detail, recorded with cameras and sketches. The astronauts' presence did not disrupt the stillness of the environment. Rather, it allowed humans to interact with an alien surface with calm observation and measured attention. Every aspect of the mission reflected decades of preparation. Decades of careful observation, experimentation, and incremental advancement had built the foundation for this moment. The lunar landing was not a sudden leap, but a continuation of centuries of scientific inquiry, engineering refinement, and patient accumulation of knowledge. It demonstrated that deliberate, steady effort could extend human presence beyond the familiar confines of Earth, opening the way for continued exploration of the solar system. After completing surface activities, astronauts returned to the lunar module for ascent and rendezvous with the orbiting command module. Every movement was deliberate, and systems were monitored continuously. Engine ignitions were carefully timed to achieve the precise velocity needed to leave the Moon's gravity and rejoin the orbiting spacecraft. Calculations for this maneuver had been prepared in advance, based on years of study, simulation, and incremental testing. The ascent stage was small and compact, designed to lift both crew and samples without exceeding the structural limits of the lander. Inside, every instrument, gauge, and control panel had a specific purpose. Astronauts followed step-by-step procedures to ensure stability, balance, and proper function. Even minor deviations were corrected calmly, drawing on extensive training and prior experience in orbital flight. Once docked with the command module, systems were checked carefully before the crew consolidated samples and prepared for the journey home. The spacecraft then followed a translunar trajectory in reverse, gradually accelerating toward Earth while maintaining steady orientation. Throughout the voyage, life support and environmental systems were observed constantly, confirming stable temperature, pressure, and oxygen levels. Daily routines were maintained to preserve health and readiness, including light exercise, monitoring vital signs, and performing scheduled equipment checks. Communication with ground teams remained steady. Telemetry, voice, and visual information were transmitted continuously, allowing engineers on Earth to confirm procedures and provide guidance. This interaction highlighted the collaborative nature of space exploration, where mission success depends on both the crew in orbit and the extensive support network on the ground. The return journey exemplified the principle that space travel relies on gradual, deliberate progress. Each orbit, each maneuver, and each procedural check reflected decades of accumulated knowledge, patient experimentation, and careful engineering. The Moon, once a distant celestial object, had become a measured waypoint in humanity's expansion into the solar system. The mission's success demonstrated that patient planning and incremental progress could extend human presence beyond Earth safely and predictably. The journey back to Earth required steady attention to detail and careful coordination. Re-entry involved transitioning from the near vacuum of space into the denser layers of Earth's atmosphere. Engineers had calculated the precise angle of entry to balance frictional heating, aerodynamic forces, and deceleration. Too steep an angle could create excessive thermal stress, while too shallow could cause the spacecraft to skip off the atmosphere. Each parameter had been refined through simulation, incremental testing, and previous mission experience. Inside the command module, astronauts followed rehearsed procedures. Instruments provided continuous data on speed, altitude, and orientation. Life support systems remained active, maintaining stable air pressure, temperature, and oxygen levels. Small adjustments were made to the spacecraft's attitude using thrusters, ensuring that it remained correctly aligned for re-entry. Even routine movements were deliberate, as loose objects could drift or interfere with controls in microgravity. As the spacecraft descended, the protective heat shield absorbed and dissipated the intense frictional energy. Layers of ablative material slowly eroded, carrying heat away from the interior. Outside, the capsule glowed gently against the pastel blue of the upper atmosphere, a controlled transformation guided by careful engineering and precise calculations. Parachutes deployed at the correct altitude to slow the module further, creating a calm, controlled descent through the final layers of air. Splashdown occurred gently in open water, with recovery teams observing from a distance, ready to assist. Astronauts emerged safely, carrying carefully collected lunar samples, scientific observations, and the quiet experience of having traveled beyond Earth. The mission's return emphasized that human space travel is the result of patient accumulation of knowledge. Each calculation, each system test, and each rehearsal contributed to the measured success of the journey. The Moon had been visited not by sudden leaps, but by deliberate, incremental progress. The achievements of these missions illustrate the careful and continuous expansion of human presence beyond Earth, showing that exploration is built on observation, experimentation, and steady refinement rather than speed or spectacle. Looking back on the history of space travel, one can appreciate it as a gradual and deliberate unfolding of human curiosity and ingenuity. From the earliest observers who watched stars shift slowly across the sky, to scholars who recorded planetary motion on clay tablets and parchment, to engineers and astronauts who expanded our reach beyond Earth, the story is one of patient accumulation. Each step built upon the previous, creating a continuous thread of understanding that slowly carried humanity into orbit, then to the Moon, and beyond. Space exploration demonstrates the power of careful observation, methodical calculation, and measured experimentation. Rockets are not launched in isolation. They are the result of decades of study, testing, and refinement. Each flight, each mission, each orbit contributes additional knowledge about physics, life support, navigation, and the human body. Even seemingly small achievements, such as a brief orbital flight or a successful re-entry, represent countless hours of planning and attentive adjustment. The Moon, once distant and unreachable, became a laboratory, a destination, and a symbol of what deliberate effort can accomplish. Human presence there relied not on sudden leaps, but on repeated refinement, simulation, and careful attention to detail. Every observation, every calculation, every cautious experiment contributed to this expansion of human experience. Beyond technical achievement, space travel encourages reflection on perspective. Seeing Earth from orbit or the Moon emphasizes both the vastness of the cosmos and the fragility of our home. It invites quiet contemplation, the kind that comes naturally when observing processes unfolding slowly over time. The history of exploration beyond Earth is not merely a story of machines and engines. It is also a story of patience, of cumulative learning, and of steady progress toward understanding and connection with the wider universe. Ultimately, the journey into space is a continuing one, grounded in centuries of observation and practice. It reminds us that progress, especially in unfamiliar realms, is most enduring when it is deliberate, measured, and attentive to the careful accumulation of knowledge. Human curiosity, paired with patience and methodical work, allows us to move forward steadily, extending presence into worlds once thought unreachable, and quietly opening the cosmos for future generations.